Next weekend, I will give you homework assignment number 1. Yeah. First, the big assignment. Small assignment. Quiz 1. Oh, sorry.
And then the homework will be due
10 days. 10 days. All right. Oh, waiting. 3 people waiting here. Yeah, all right. Part D, solution by variation parameters. Yeah. D.1. Yeah, before we get to our main topic today, I like to talk about 2 questions we did last time. Yeah, because last time we didn't have enough time to explain. So let me explain these 2 questions first. First one, that resonance problem, understand the resonance. Because I want to do the calculation to show you why it caused some big problem. Yeah, because this one, for engineers, it's an important consideration. Okay? So you have to consider, when you solve real-world problems, you have to consider this one. Yeah. All right. So the first question, yeah, let's revisit that question we did last time. Problem 9, undamped forced oscillation with resonance. We did half of the problem last time, right? Yeah. But today, this one, I want to complete the remaining half. But when I do it, look at the question. We need to work for what frequency of the driving force would you get resonance? We want to answer this question. Yeah. To do that, we have to change the omega. The version we had last time, the omega is 1, right? Omega is 1. So here, I change omega 1 to a variable omega. Okay? Yeah, because if it's 1 fixed, then we cannot change anything. Right? Yeah? But here, the question, we need to change omega to calculate the frequency that causes the resonance problem. So we need to change it. Yeah. So the first change the omega. Okay? Then let's solve the same problem with this unknown omega. Yeah. All right. Solution. The same equation, but we add omega. Right-hand side function, cosine, sine, with unknown omega. Okay? Yeah. Which one would cause some severe problem? Yeah. Let's see. Initial values to initial values. First, do you know to choose this special pattern for the particular solution? When you look at the right-hand side function, cosine, sine, so our particular function should have the similar pattern structure, right? So it is natural. Yeah. Later I will do a summary, show you for what functions you should choose what type of particular solution. Yeah. Later we will have that part. Here, A, B to be determined. Yeah. Coefficient to be determined. All right? Yeah. Let's take derivative. Yp prime, easy to calculate. Yp double prime, that one. Yeah. Then let's go back to the original equation. Yeah. and comparing the coefficient. Yeah, so this is the original equation, but we need to replace. Yeah, we need to use our new expressions to plug in and compare left-hand side, right-hand side coefficients. Compare the coefficients of cosine omega t and the coefficients of sine omega t, and each one, it should be the same. Yeah. Do you know why we can do this? Why we should do in this way? Any idea? Compare the corresponding coefficients for cosine, for sine. Any rationale behind it? Right? Yeah. Partially correct. Yeah. Reason is they are bases. Cosine, sine, basis. When we have expression, yeah. So here, the same value can be represented by the basis in two different ways. Okay, two different ways, because since they are bases, so the coefficient of the individual function in the basis must be the same. The basis reason. If it's not basis, then you cannot do this. Okay? Only when you're working on basis you can do it. Okay? All right. Yeah. By coefficient comparison, we can find, after simplification, little a, undetermined. So this time it can be written as omega expression. Okay? Yeah. Fraction omega squared at the denominator. B, another fraction omega squared at the bottom. Okay? Can you see anything special after this? When we have AB, we can go back to get the y particular solution. Yeah. Here you can see when omega equals 3, what happens? Yeah. Or let me say it this way: when omega very close to 3, not exactly 3, very close to 3. How about that? What would you get? Yeah, very big number. Very big number. Look at here. A very big number. B very big number. Y represents the displacement, right? So very big. Think about your system. What happened to your system? Okay? We can understand like crash. Well, something like, the system resonance causes some disaster. Okay? Yeah. Because your displacement cannot be, that wild, right? Yeah. So here you can see, from the formula, we can see the problem occurs when omega close to 3. Not necessarily exact 3. It can already break the system.
This might be a stupid question. What exactly is
Resonance?
resonance?
Yeah, so that's, all right. Some external forces causes some impact, that severely damage the system. Yeah. In physics, I don't know if you did experiments like this. Some example.
Sound.
Yeah, sound.
Whenever you hear ringing,
Yeah.
because the atoms in there are
Right.
vibrating.
Right. When the frequency very close, the vibrating, much bigger. Yeah. That phenomenon. Yeah, physics.
Resonance is why you can sing and break a fly glass.
Yeah.
Yeah.
The glass, right.
Yeah.
That glass, right. Yeah. That experiment. Yeah. Yeah. Yes. Yeah. That kind of thing. So here, from math, we can see why is that. Okay. Yeah. Very good. So when you design a system, try to avoid that. Yeah. Actually, here the 3. If we go back to last time, we call it the 3 is the natural frequency. Yeah. Because 3, if you solve the homogeneous, you will get omega equals 3. Omega 0 equals 3. Yeah. Because here, the characteristic equation from this part. Oh, I need, anyway. Yeah. From this part, if we only look at the homogeneous part, after simplification, look at multiply 8. We can multiply 8. What would you get? Lambda squared plus 9, right? Plus 9 equals 0. Okay? So what's the lambda? 1, 2. Yeah, sorry. Yeah. Because you have 2 lambdas. 1, 2 equals plus minus 3i, right? 3i corresponds to cosine 3t sine 3t, right? That 3, that's the, corresponds to the natural frequency. Okay? Yeah? So from our calculation, it tells us when the external force frequency, here, external force frequency close to the natural frequency, then we would have that resonance problem. Yeah. So that and complete the question we talked about last time. Yeah. So we try to, get better understanding. Yeah. So that's the first part. Second part, another question I didn't elaborate much last time, due to the time limit. Now let me elaborate more. Second question, I use one example. So here, answer, the final answer, we need to calculate the frequency, right? So omega, we use 3, but you need to divide it by 2 pi to get real frequency number. Yeah. By the definition of frequency, this is the frequency formula. Okay, the period formula, reciprocal 2 pi omega. That's the period. Okay, yeah. All right, yeah. Oh, another. All right, D.2. This topic. Undetermined coefficients for appropriate structures. Now, let's look at this example. Exponential function input again. I modify our question. Remember last time, Ian asked me question, right? Yeah, you asked. I remember that C. Remember that capital C, cx squared. Yeah, let's look at this question. Last time we did a different question, but that one, when we compare coefficients, two coefficients happen to be 0. Remember? Then Ian asked me, so if it's not 0, what will happen? Now, let me answer that. Because first, the general answer is, if not 0, your structure assumption is wrong. So you have to make the correct structure assumption. Yeah. Here, I show you how to make correct structure assumption. Yeah. Here, similar question, but I intentionally modify such that, if we use our old structure, it would be wrong. Okay? So we have to make correct structure assumption here. Yeah. All right. First, to find a particular solution, this time, look at how do I make the structure assumption. Last time, we only used the last c x squared term, right? Yeah. Yeah. To be safer, we should use whole quadratic formula. All three terms for the whole quadratic formula. Yeah. Yeah, because here, e and double prime, so that, you know, the order, the degree should be 2. Corresponds to the double prime. Yeah. So we should set 3 undetermined coefficients, not just 1. If your assumption could be wrong. Yeah. If 3, we know 3 covers all the possible cases, right? A quadratic formula, the general quadratic formula, we cover all possible quadratic formulas. Yeah. If 1, you only talk about a special case. Yeah. All right, so now with A, B, C to be determined, let's take derivative, yeah. Double derivative here, yeah, yeah. Then put it back to the original equation, yeah, all right. After simplification, yeah, we compare the corresponding coefficients. Yeah, yeah. Here still, x squared, the coefficient is 0, yeah, yeah, because, you know, cancel out, yeah, cancel out, yeah, yeah. You may ask me if now it's 0, right? If now 0, then this method does not work. Yeah. Does not work. Yeah. All right. So we find B, C. Where is A? We couldn't find A. Nothing about A. What does that mean? Yeah, yeah, partially correct. So first, nothing, no restriction on A. That means A could be any number, right? Any number, it is true. Any number is. But here, remember, we only need to find a particular solution. A can take any number. Why we just take it 0? The simplest. Because we just want to get one particular solution. Yeah. So we just take A equals 0. Okay? So we can write this particular solution out, this one. Then, homogeneous general solution, that's easy, homogeneous. Okay? Yeah. To find the general solution, we look at the characteristic equation, lambda. It's a double, not double, yeah, 2 real roots. Okay, yeah. -1, -2, 2 real roots. Yeah. So then the general solution C1 x to the negative x, C2 e to the negative 2x. Yeah. All right. Then the particular solution added up. Added to it. Okay? All right. Now you can see why a value is not important, right? Because look at C1 part. Yeah? E to the negative x, e to the negative x, a part repeated in the C1 part, right? Yeah? A constant number, we can move in and out C1. How about that? Yeah. That's why we can take any A number. We only just change C1. Okay? Just like we change C1. All right. All right. Then, with the initial conditions, we can plug in to, after some calculation, we get a C1 equals 1, C2 equals 0. Yeah. So the final solution is this. Yeah. 1 minus 2x plus 3x squared times e to the negative x. Yeah. Yeah. So after this example, later you will see when you write the form for your particular solution, yeah, you should write in this way. Okay? Yeah. Quadratic function times that e function, yeah, because second order, yeah, so for this pattern, yeah, so you should use the quadratic function. Okay? Yeah.
Just to be clear, is that solution supposed to be y or y?
Y, yeah, good, yeah. YP, yeah, that's that one. Oh, yeah, that one. Yeah, solution. Yeah, good question. So it's better. Yeah, we write y. Yeah, because YP we treat it as an intermediate solution. Okay, this y is the final answer. That is the intermediate step. Yeah. Intermediate step. Okay. Although you can say if this YP it is also a particular solution of the original equation. That's also correct. Yeah. But we do not want to confuse with our previous YP. Yeah. Yeah. Previous YP. Yeah. Good. Yeah. This should be Y. Okay. Yeah. Very good. All right. So after this, then, all right, we need to do a summary. Choice rules for method. Oh, yeah. This choice rule for method, yeah. Yeah, actually, yeah, so here, yeah. Because by the choice rules for method of undetermined coefficients, yes. Oh, after I finish that, so I may need to go back to our previous. Yeah. So let me go back to the previous. Yeah. Previous, yeah. All right. Actually, this quadratic, you can see we make this assumption, yeah. Actually, here you can see the square coefficient is 0. Square coefficient is 0. Okay? Yeah? Yeah. So that means, when we make assumption, we should not include the square term. Because this parenthesis, there is no square term. Parenthesis, there is no square term. Okay? Yeah. All right. Yeah. Later, let's go to look at the choice rules. Yeah. So we will see from choice rules, we will see what pattern, so what form should we take. Yeah. All right. Yeah. Here, let me show you. So the table here, all right. First, the table here, term in R of x, right-hand side function, the current method, the method we are using, method of undetermined coefficients, can only handle these functions. If the functions other than these functions, then that method would not work. Would not work. Only for these special functions, that method. Okay? Yeah. And combination of these functions, also okay. Yeah. So then it tells us when you see the first one, when you make choice for YP, should use here. Okay? It gives you this explicit form. Okay? YP. Yeah. YP form. Then look at that. Yeah. X monomial x to the n, then x to the n, you know, this polynomial, the highest order, the same as the order of that one. Okay? Same order as that one. This tells you something, okay? If the quadratic function here, then quadratic function here. If a linear function there, linear function here, okay? Same order, yeah. Same order, yeah. All right. Then for, you know, other cases, yeah. All right. Yeah, but yeah. So then let's look at these three rules. Yeah. First one, basic rule. If R function in 4, I give you the equation 4. Okay, this is equation 4. Yeah. R function in equation 4 is one of the functions in the first column in table 2.1. Choose YP in the same line and determine its undetermined coefficients by substituting the remaining work. B, modification rule. If a term in your choice for YP happens to be a solution of the homogeneous ODE corresponding to 4, multiply this term by x or by x squared if this solution corresponding to a double of carries, yeah. So that's right. Yeah. So because YP, all right, YP here, it may happen to be the solution of the homogeneous equation. Then, when we use homogeneous, we know, we can multiply, multiply for the double roots or by x squared, because double roots of the characteristic, x squared, here yx squared, right, to see, I think, to see that modification rule better, so we may need to find an example, see it from an example, here too abstract, all right. Sum rule, if R of x is sum of functions in the first column, okay, then WP, we also take the sum of the functions corresponding lines of the second column. That's easy to understand. This modification rule a little hard to understand. So if I find the example, so I can talk about, we can come back to look at the modification rule. All right, so so based on this summary, so I think we can solve differential equations following these format. Okay, all right, Next, problem 10. This one, gun barrel. Look at this question. Here we make a model for this gun barrel. So this part, okay, shoot gun. Okay, so there is a force, gunpowder, chemical force. There is a force. The force given with this function, because the force, push on the shell in a certain period, So here we use the period from 0 to pi. There is a force, okay? Force. After the bullet get out of the gun barrel, there is no force. right? No force. So after that point, the force equals 0. Force equal to 0. Okay? No force. Okay? Yeah. All right. Yeah. So the equation, differential equation, yeah. So here we model this gun barrel. Okay. Not that bullet. Yeah, this gun barrel, this part. Okay. We model this part. But due to that force, so there is a, displacement. Yeah. Motion. Yeah. Motion. Moving forward. Okay. Forward. So use this spring to slow down. Yeah. So this as the model. Yeah. All right. So heavy spring breaking the barrel. Okay. Yeah. So the K coefficient of the spring is 1. So the equation is y prime plus K equals 1. 1 times y. Yeah. Undamped. Our assumption the system is undamped. Yeah. So the y prime term is gone. No y prime term. Undamped. All right. So there. Yeah. After that pi, the force equals 0. Force equals 0 during the period from t after pi and goes to infinity. That period, force equals 0. Yeah. Then initial conditions. Yeah. All right. So now we need to calculate the y function. Calculate the y function to solve. Yeah. Yeah. All right. Yeah. So how to solve this ODE? Yeah. Look at the function at the right hand side. What is that function? What is that function at the right hand side? Polynomial, right? Quadratic polynomial, right? Yeah. So when we make our YP, what function should we use as YP? YP function. Recall the rule, the choice rule. The choice rule. Second line. What function should we use for the YP function? Simple, right? Yeah, here, let me write out. YP, how about this function? Quadratic function. Because the highest degree is 2. Okay? Highest degree is 2. Yeah. Although the, degree 1 term is missing. Yeah. Yeah. But we just use it anyway. Yeah. Right? Yeah. Then we take first derivative, second derivative. Pretty simple. Yeah. So let's put it back to the original equation. Yeah. That b is gone. Yeah, because right hand side no t term. So b equals 0. Yeah. Other than that, c equals this negative 1 over pi squared. You compare the corresponding coefficients for their individual terms. Yeah. Again, why we can do this kind of comparison? Can you explain? T's coefficient, t squared's coefficient, constant, why we can compare? Basis again. Basis. Yeah. Here the basis, okay? Yeah. So let me write a basis. Yeah. So you need to have the strong strong impression for the basis concept. Yeah. Here the basis. The basis we're using one t squared. Okay, 1t squared. 1 for the constant term, 1. Then t, linear term, t squared, quadratic term. Okay, that simple basis. So we can compare their corresponding coefficients. Okay, yeah. All right. So then, here, the basis, it does not mean the basis of the solution. Okay, the basis of the functions of the quadratic polynomials. Because basis we can use on many things. Yeah. So here, do not use the basis for the differential equation, the solution. Yeah. Solution, that's the one place we can use basis. Other places, we can also use basis, right? In our linear algebra, we use basis everywhere. But linear algebra, there is no differential solution, right? Yeah. So the basis we can use in much broader situations. Yeah. All right. So we get the C, B, and A. Then our particular solution can be written explicitly in this way. All right? Yeah. But that's the particular solution. So we need to do the general solution part, the homogeneous. That part we can see easily. Yeah? Sine, cosine, capital A, capital B, two coefficients to be determined. Then we use two initial conditions to determine capital A, capital B. Okay? Yeah. All right. Yeah. So here I just do the continuation. Yeah. All right. To determine A, we plug in the first initial condition. Yeah. Y of 0 equals 0. Yeah. So you get A equals this number. Then for B, we take a derivative. Then we plug in 0 value. Yeah. So B equals 0. Yeah. All right. Yeah. Yeah. Then we can write Y function. Yeah. Yeah. So here we use Y. Yeah, not YP. Yeah. So our final solution Y equals this expression. Yeah. Cool. Understood. All right. Yeah. Okay. Yeah. But is it the final solution? When you look at this, so here we get this one. Look at the whole question. Is it the final solution? Y of t? Yeah. It is part of the solution for the interval t between 0 and pi, right? For t after pi, we cannot use that equation, right? We have to modify the equation. Yeah. So that's the only partial solution on that interval between 0 pi. Solution between 0 and pi. Okay? Yeah. Yeah. So we need to specify the t interval. Yeah. And this is our first piece of solution. We need to calculate the second piece to get a whole solution. Yeah. How to calculate the second piece? Yeah. The second piece, t after pi. After pi, that's the second piece. But the second piece, the force is gone. No force. F equals 0. So we should modify our equation, the right-hand side 0 force. So we solve this equation. It's simple, right? We can solve it. Yeah. the general solution to undetermined constant C, D, C cosine t, and D sine t. But we need to find C and D to complete the solution. Now, question: how to determine C and D? Yeah. So we need to get information from the original problem. Because to determine these coefficients, we need to use initial conditions, right? Yeah. Usually we apply initial conditions to get those undetermined coefficients. How do we get initial conditions for this second piece solution? Yeah. From the given question, we cannot see explicitly the initial condition for the second piece. We only have initial condition for the first piece, but not second piece. Yeah. Can you use your logic reasoning to get initial conditions for the second piece? Good. Good. That's the critical point. Plug in pi. All right. Plug in pi. So here we make assumption. Yeah. The displacement function, y displacement function, yeah. Y displacement function, you know, the display for this gun barrel should be continuous. Displacement function should be continuous. Okay? Yeah. Because you cannot jump. Right? You have to move, the movement has to be smooth, right? Although, you know, you can stop fast, but still it's a smooth curve, right? Y function, yeah, think about y function should be a smooth curve. It cannot have breaks like this, right? You know, like, you know, cliff, right? Like this. That's not reasonable, right? Has to be smooth, okay? Sharp turn, but still a curve, okay? Continuous. So we can make a reasonable assumption. Y function must be a continuous function. Then we plug in pi for the first piece. Is this should be the initial value of the second piece? The end of first piece should be the same, should be the starting point of the second piece. How about that? End of the first piece. End. Okay? All right? And the second piece. So the first piece, second piece should be connected with a continuous function. Should not, there is no break between them, right? Yeah? Should be connected. Okay? All right. The same thing should be true for derivative. Derivative should also be a continuous function. Okay? Yeah. Your derivative changes continuously. Okay? Yeah. Yeah. Because why the derivative must be continuous? Because second derivative exists. If the derivative is not continuous, then you cannot take second derivative. Second derivative can only be applied on a continuous function of the derivative. Yeah. So the derivative must be continuous. Otherwise, no second derivative. Okay? Yeah. All right. So with that assumption, yeah, that's assumption, you know, can be justified. Yeah. So we take pi values from first piece. Plug in pi from first piece. Okay. Solution. Yeah. And y prime also from first piece. So we get initial conditions for the second piece. Yeah. So then we plug in pi. CD should be the same as these two values. Yeah. Y prime. Then plug in pi. So we get a capital C. Plugging pi into the derivative, we get that. So here, I want to check your basics. So when we plug in pi, Are you familiar with sine pi, cosine pi value? You feel okay? Yeah. In my basic formula table, I put all there. Yeah. If not, just refresh your memory. Yeah. So what is cosine pi? Cosine pi.
Oh, yeah, excellent.
Good. Perfect. Yeah. Perfect. Sine pi.
0.
Good. Great. Super. Yeah. All right. Yeah. All right. Yeah. So the final solution, this is second piece. This is for the interval t greater than pi, the second piece. So the final solution, you should combine these two pieces. Yeah. So we call it piecewise function. It's a piecewise function. Two pieces. Yeah. Piecewise continuous function. Yeah. All right? Yeah. So later, when you see, situation like this, you have several pieces. You need to solve piece by piece. Yeah. Okay? Yeah. All right, so we finish that one. D.4. Now, the main topic of this part, solution by variation parameters. Yeah. All right. Method of variation parameters, part 1. Yeah. Let me describe. Yeah. So this part, much harder than that method of undetermined coefficients. That part, that's pretty simple. But this one, here we need to do a lot of calculation. Okay. I hope you can follow my calculation. But at the end, we just apply formulas. So you do not need to repeat all the derivation here. Yeah. After we derive those formulas, then we just apply formulas. All right, standard form. This time we want to solve the non-homogeneous equation like this. Yeah. And to find a solution, yeah, we want to find a particular solution, YP. So this method actually give you some, very smart way to find a YP solution. Yeah. For the homogeneous, here, it assumes you already have the homogeneous solution. Homogeneous, yeah. Actually, you can see, yeah, before we work on the, the whole derivation, look at, suppose R of x equals 0, we have homogeneous, but if P and Q not constant, is it easy to find a solution homogeneous? P function, Q function, not 0, not constant. It's hard, right? Yeah. Because currently we can only do the constant case. The formulas we derived only for constant case. For general PQ, we don't have any formula, right? We don't. Yeah. So that part may not be easy. That part still could be hard. Yeah. That part still could be hard. Yeah. The general, even homogeneous. Yeah. Yeah. All right. Now we consider the homogeneous equation, but for this method, we assume we already have y1, y2. Yeah. If we don't have y1, y2, then this method does not work. But if you have the y1, y2 solution, then it must work. Okay? Because the formula is there. Okay? We will get the formula. Yeah. All right. Variation parameter. So here, let me try to explain what special format of P we should use. Yeah. That assumption is important. What P should we use? That assumption is important. Yeah. Yeah. Here, it's not easy to get the right assumption. Yeah. Yeah. Because usually when mathematicians develop this method, they try many different ways, sometimes without any specific purposes. Just to try random things. Okay? Yeah. Many times scientists, they do experiments doing some random testing, right? Yeah. Because many times you do not have logic. Just try random things. Yeah. Mathematicians, they also try some random ideas, you know, this type, that type, which one works. Yeah. Yeah. So this here, we consider here. Yeah. Although I can explain a little bit, but still, you need to do some experiments to see if it works. Yeah. All right. So here, let's start with the homogeneous equation, but for the, so here, yeah, look at that. Because y1, y2, they are the basis for the homogeneous equation. So the general solution YH in this form, C1, Y1, C2, Y2. Yeah, that's no problem. By the linearity property or linearity principle or superposition principle, no problem, right? Yeah. But in the first look, it does not help, right? How can this one help us? Yeah, yeah. But next step, replace the parameter. Here, C1 parameter, C2 parameter, but these two parameters, they both constant, right? They both constant. Yeah. Here, look at the how mathematicians, they play magic here. They play magic here. Yeah? Yeah? Because based on our whole old theory, general solution, we should use constant right here, right? The general solution. But here they make some wild manipulation. Okay? Yeah, sometimes you need to do that. Yeah. Very wild manipulation. Then replace C1 and C2 by two undetermined functions. How about that? U function, V function. Replace two constants by two functions. How about that idea? How about that idea? Is this some brave step? Yeah. First, we know U function, V function more general than two constant, right? More general. Yeah. Because constant you can treat as a special U function, special V function, right? Only constant term. U function, you know, could be very complicated U function, V function. So you have much more freedom, right? In U function, V function, you have more freedom. When you have more freedom, you can do more, right? Yeah, you can do more. Yeah. Here we want to do more, right? Yeah. Here we want this YP. Here, remember, YH. When we start, we use YH. But suddenly we switch to YP here. Okay? This is YH, but here it becomes YP. How do you connect YH to YP? Okay? That step, wild, right? Yeah? But it works. It works. Yeah. So here you can see scientists, sometimes they make some wild moves, but result. It works. That's good. It works. Yeah. So you make some ridiculous, because by logic, it looks like no logic between these two, right? What's the logic? From YH to YP, what's the logic? Okay. YH is for homogeneous. YH, this one is for the homogeneous. But YP is for the whole original non-homogeneous equation. What's the logic? No logic, right? No logic. No. You can only say partially connected, because this part, that part, connected. Partially connected. Partially connected. Okay? All right. Yeah. All right. To make it a particular solution of the original ODE. Yeah. All right. Yeah. Now, let's take first derivative. Yeah. Because after you assume your YP has this form, then you can take the first derivative by product rule on the first product, product rule on the second product. Okay? So you have four terms. Four terms. Is it complicated? Yeah. You like to say that, yeah. Yeah. Do we like the complexity? No, nobody likes the complexity. So next question. Can we simplify it? Make it simpler? Make it simpler? That's our next step, next task. All right. Let's take a break. When you come back, let's look at the remaining of the story. Yeah.